Good morning. This is lecture number 27. We are starting a new module, module 5, matrix analysis of beams and grids. So, if you recall, we finished 4 modules. In the last module, we showed how the stiffness method and the flexibility method can be applied to structures with axial elements. Now we look at beams and grids. Here again we will show how the conventional stiffness method, the reduced stiffness method and the flexibility method can be applied to beams, and we will restrict the application of only the stiffness method, especially the reduced stiffness method, to grids. What's the difference between a beam element and a grid element? What's the difference between beam element and grid element? I have shown you a beam element here. There are only 2 internal forces or force resultants at any section. One is a shear force, the other is a bending moment. The bending moment here is shown in the vertical plane, and you get shear forces only if you have a variation in the bending moment. The grid element is this element plus something extra. What is it? Torsion. That's right. So that's the grid element. The grid element is the beam element plus some torsion. We will look at this at the end of this module. This is covered in the section on beams and grids in the book on advanced structural analysis. So as in earlier cases, we have 3 methods: the conventional stiffness method, the reduced element stiffness method and the flexibility method. We will begin with the conventional stiffness method. It becomes easier now because you already have a taste of this. We saw how it was applied to trusses, but now with higher order elements you will find the work is a little more, because the element stiffness matrix itself becomes larger. Imagine a space frame element. It's a 12 by 12 element stiffness matrix. So we will keep that till the end, but we will move slowly. Here you have 4 degrees of freedom. We have looked at this element earlier. Now this is a prismatic beam element. Length is Li in the ith element. Flexural rigidity is constant EI. Can you write down from first principles, from the physical approach, can you write down the 4 by 4 element stiffness matrix for this element? I will show you how this can be derived in many ways, but you already know the answers. You can try drawing the 4 sketches. Just write down that 4 by 4 element stiffness matrix for the sign convention we are following here. 4 degrees of freedom, 1 star and 3 star in the local coordinate system refer to translations or deflections at the 2 ends. 2 star and 4 star refer to end moments or rotations, slopes. If you recall, when we did the displacement method initially, when we looked at the historical development of this method, when we looked at slope deflection method and moment distribution method, the sign convention was clockwise positive. Why did we switch to anti-clockwise positive in the matrix method? Because we were wanting to follow the laws of vector algebra. Our Cartesian coordinate systems we chose as x, y, z, and I cross j must be equal to k. So that is why we did this slight switch, but do not get confused. Also, if you recall, when we did slope deflection method and moment distribution method, we did not really include the deflections as in our slope deflection equations as unknowns, right, except when they were known chord rotations. But in the stiffness method we include everything. except in the reduced element stiffness method. So you have a 4 by 4 element stiffness matrix and I want you to generate it on your own. Well, you must realize that we have restricted the degrees of freedom only to the two ends of this element. Is that justified? If you take any location x star in that beam, that point inside that beam, that has a deflection delta x star. Can we write that delta x star in terms of d1 star, d2 star, d3 star and d4 star as shown? Only then we are justified in limiting the degrees of freedom to 4. Can we do this? How do we do it? How do we do it? Well, in a classic displacement approach we do not know moments. Moments are at the tail end of the derivation. We do not know moments. So if I have to go by this argument, then it follows that the displacement function delta x star can be a polynomial, but of what order? No, it does not depend on loading. This is displacement method. If I know d1 star, d2 star, d3 star, d4 star, in terms of these 4 end displacements, can I write an expression for delta? That is a displacement approach. I can write a polynomial equation. Yes or no? What will be the order of that polynomial? Okay, let me make it even simpler. Let us say you are doing a laboratory experiment. Okay, you are trying to discover some relationship between y and x. X is your independent variable, y is your dependent variable. You are able to do 4 experiments. You play with the value of x, you have x1, x2, x3, x4 and you get 4 values of y, y1, y2, y3, y4. Then you try to plot and you hope that you get a smooth relationship, right. If these 4 points are exact, you will be able to get some curve. You can try to fit a polynomial. What is the highest order of polynomial you can fix with the data that you have? You have 4 points. If it is a straight line, how many points do you need? 2. So you got 4 points. So it is a it's a cubic polynomial. So this is the kind of thinking that you need to develop. Here you want to write an expression for deflection at any location within the beam, delta as a function of x star. You are making a statement that all I need to know are the end movements. That means I need to know the deflection and the slope in the direction shown at the 2 ends. With that information alone, I can write down an expression for delta. So if you do by the displacement approach, what is the order of the polynomial that you can do? It is going to be a cubic polynomial. The next question now we ask is that true or is it approximate? We are now digging a little deep into the subject. You will find that finite element analysis, which is something you will study in an advanced course, uses such displacement functions to develop the theory. Okay, you have a complicated structure, you break it up into small parts, they are called finite elements, and you try to reduce your degrees of freedom to the movements at the ends of the element, and you have to interpolate to get the information within the element, and if you are lucky you have got an exact formulation, in which case you get an exact solution. Now let us talk about finite element analysis of a plane frame. Okay, you have beam elements or let us say plane frame elements. The usual assumption is if you have an approximate displacement function, the finer you make your mesh, the more accurate your results. But is that what we do when we do a plane frame analysis or even a space frame analysis? Is it enough to take just the beams and columns from the beam column joint, from one joint to the other joint, and have just one element, or do we need to divide it into say 10 elements, one single beam or column into 10 elements in the interest of greater accuracy? No, you will find in practice people just limit it to single element, right, and they get the exact results, which means the displacement function on which you are deriving your stiffness matrix from first principles must be exact. Why is the displacement function exact? In the case of a prismatic beam element. Incidentally, we can do a similar derivation for the truss element. We have a linearly varying displacement function because the strain is constant if you have a constant force. So that is justified. Here how is it justified? So I want you to think, you have to finally bring it to bending moments, right. In the slope deflection method of analysis, we were happy with the end moments being unknown, and we write the end moments in terms of slopes and deflections, and we get the end moments, and then we get the moment in between at any point by interpolating the end moments, right, because your beam is reduced to a simply supported beam. Agreed? So what is the variation of bending moment? That linear, as long as you do not have intermediate loads. So we are trying to get rid of intermediate loads in all displacement methods through equivalent joint loads. So your bending moment can have two different values. Here also you have F2 star and F4 star, they need not be the same. So you have a linear interpolation between the two end moments to get the bending moment at any section. Can you use that? Curvature is linear. So slope is quadratically varying, and so deflection. So there is a, you are dealing with an exact function. Okay, good. So you could write the deflection at any point, the slope at any point x star, and the curvature at any point in terms of those four end displacement using some functions which are called displacement functions, sometimes called trial functions in finite element analysis, because in a plate element, for example, you do not have it exact. So it's a good approximation that you make. So it's called a trial function. This is no trial, this is exact, and we'll prove it. So those are displacements, and these are the forces, and there's a relationship from the displacements. You can get an expression for curvature. Okay, if you have a cubic variation for displacement, the curvature will have a linear variation. If you multiply the curvature at any location by the flexural rigidity EI, what do you get? You get bending moment. Okay, this is the displacement approach, and if you take the derivative of the bending moment, you get the shear force, right. And so if you apply the boundary conditions at the two ends to bending moment and shear force, you get F1 star, F2 star, F3 star, F4 star. So there is a beautiful relationship. Let us work on this. Okay, so let us get the physical meanings of the four columns in your stiffness matrix. In the first column you apply D1 star equal to 1 and you arrest the other degrees of freedom. This is a picture that you get, right. The next one you apply D2 star equal to 1. We have done this before, so that is a picture you get. Next you apply D3 star equal to 1, D4 star equal to 1. You get those same deflected shapes flipped over either laterally or vertically. Okay. From this, can you pull out the definitions of stiffness coefficient? Well, you can, but first you write down an expression for deflection. You have 4 boundary conditions, write down an expression for slope, apply the boundary conditions, and you can actually get equations for these deflected shapes. I have shown you 4 deflected shapes and I am making a tall claim. The claim is any arbitrary deflection in that beam can be obtained as a weighted average of these 4 shapes, right. Let us prove it. Well, you can substitute the boundary conditions. Which boundary conditions? That at the 2 ends, when x star is 0, the deflection is d1 star, and when x star is L, the deflection is d3 star. That is the definition of deflection, right. Similarly, you can write for the slopes, and so you can actually go through first principles. I am not asking you to do it, I am just giving you an introduction to what you will need to do later in finite element analysis. You do not need to do it, but this is the theoretical background. You can actually generate these equations not bringing any statics into the picture. We did not even bring flexural rigidity here, shear geometry, shear curve fitting. I have 4 expressions, all of them are cubic. They technically they are cubic Hermitian polynomials, okay, and these are those 4 expressions, okay. You do not need to memorize them, but you should know that they can be derived from first principles by simple mathematics using the polynomial function. You have 4 constants, 4 boundary conditions, either the deflection or the slope is 0 or 1, plug them in, solve for these equations, you will get. So you get an expression for delta, you get an expression for theta, you get an expression for phi, the curvature. Curvature will be varying linearly, slope will be varying quadratically, and deflection will have a cubic variation. These displacement functions can be used to generate the element stiffness matrix from first principles, okay. How do we do that? So we have these functions, and we have these relationships from relating bending moment to curvature. Plug in those boundary conditions in terms of x star equal to 0, F1 star will give you a shear force, F2 star will give you a moment, and so on. So if you plug this in, you can actually generate the solution. So there are many ways of doing it. This is one way. It's not the best way, I mean, for people who are very comfortable with statics, but let us say you had a non-prismatic beam element, a tapered beam element, okay, then such methods will be very effective, okay. So there are many ways of doing it. One is a physical approach, which is something that I would like you to do. You know exactly how it is going to behave. You can write down the stiffness values. The other is the displacement based approach, which we just took a look at. Third is an energy formulation, which is also displacement based, and the fourth is a force based approach. At least I want to cover the theory behind these 4 approaches, but this is what you would get in the physical approach. Let us check it out. Take the first column. The first column is what you get when you apply d1 star equal to 1, okay. So let us look at that. If I lift this up by unity, but I do not allow a slope there, and I do not allow any deflection here and a slope here, you can visualize the behavior you get. You get a chord rotation, right. When I lift this up, I get a chord rotation. I get a chord rotation. What is the value of the chord rotation? Chord rotation is only joining the 2 ends with a straight line. That is the meaning of chord. You are right, flexural rotation is 0, chord rotation, so it is 1 by L. Is the chord rotation clockwise or anti-clockwise? The chord rotation is clockwise, right. If I have a clockwise chord rotation, what are the end moments I get? Anti-clockwise, which means they will be positive. And what will be the value of those anti-clockwise chord moments? 6 EI by L squared. Remember we derived all this, and that is the reason why F2 star in this first column is 6 EI by L squared and F4 star is 6 EI by L squared. Clockwise is positive in this new sign convention, and if these end moments are known, then the shear forces are the sum of these two divided by L. You will always, so you will get 12 EI by L cube, and the diagonal element will be positive, the off diagonal will be negative. Now you take the third column. In the third column you lift up D3 star. What is the chord rotation you get? Anti-clockwise, minus 1 by L. So you get clockwise end moments. So both the end moments will be negative. That is why you get minus 6 EI by L squared, minus 6 EI by L squared. Shear forces will be plus and minus. Remember the diagonal element will be always positive, off diagonal. So I have given you a simple technique where you do not need to do anything but use your brains and fill up those. Can you fill up the first and third? You got it? The second column, let us see. Second column is, imagine you are giving a unit rotation here. Can you remember the deflected shape? It is a simple shape. You are arresting all the degrees of freedom. What is the moment that you need to get that unit rotation? 4 EI by L. What is the carryover moment at the other end? 2 EI by L. So both are positive, 4 EI by L here, 2 EI by L here, and they are both anti-clockwise. So you will have a couple. You will have a couple. What is the shear force you get? 4 plus 2, 6 EI by L squared, and you should know which is positive and which is negative, and likewise you can finish the fourth column. The fourth column you give a unit rotation. This is the physical approach, and I want you to be strong in the physical approach, and it is exact, you know that. Okay, another interesting thing you can notice is this is a beautiful square symmetric matrix. It is a square symmetric matrix. From the physical approach, force based, we can derive it, but we can also derive it from the displacement based approach. Assume the displacement function, plug in those boundary conditions which we discussed, you will get the same answer. Okay. So these are the definitions of K11 star, 22 star, 31 star, 41 star. I have put in green color the second subscript, because that is where I am applying the unit displacement. Is it clear? So it's, you remember when I have Kij, the cause is always in the second term, the effect is at the first term location. So when I apply D1 star equal to 1 here, this 1 star will appear in all my stiffness coefficients in the second term, and the first term matches with the coordinate that I am dealing with. Is this clear? This is a physical meaning. I have the curvature from my earlier derivation, and I plug in those boundary conditions, I get these answers. Okay. If I do the same thing for D3 star equal to 1, which is the same deflected shape flipped over, I get the same equation. From first principles, by the way, without, how did I do this? You do it, I have done it, it is there in the book. You got the curvature equation, you put x star equal to 0, you will get the two end moments, and x star equal to L, plug in those boundary conditions, there are your stiffness coefficients. You are finding it difficult? See, this we have derived. If you multiply this with EI, what do you get? Bending moment. Put x star equal to 0, you will get the moment here. Okay, sagging positive, so you have to put the correct sign. You put x star equal to L, you will get the moment here. You take the derivative of the bending moment expression, you get the shear force. In that expression, put x star equal to 0, you will get this quantity, and put x star equal to L with a minus sign, you get this quantity. That is the way to do it in the displacement method. Did you get it? I just want you to get the hang of the theory for future applications. Got it? So this is the displacement approach. We calculate the bending moments and shear forces not in the beginning, but at the fag end after we get the curvatures. And so you can do this derivation for all the 4 cases, you get exactly the same results. So we have done 2 alternative ways of deriving this element stiffness matrix. One is the force approach, physically we understand what is going on, we just write down those values. Second is we pretend we do not know statics and we know only geometry, we know only kinematics, we derive a shape function or displacement function, take the derivative of it, get the rotation, take another derivative of it, get the curvature, multiply it by EI, get an expression of bending moment, plug in the static boundary conditions, take the slope of that expression of bending moment, get an expression of shear force, plug in the 2 extreme values, put the boundary condition, I get the same. So it's beautiful, and this is how it is done for difficult problems. If you want to do first principle displacement based approach, this is the basis for that. There is an energy formulation, it is discussed in the book, you can read it. In the energy method you have to write an expression for strain energy. Once you have a displacement function, and in this case you have got an exact displacement function, you have got an exact expression for strain energy. Now you know that you can pull out the stiffness coefficient from the strain energy by the mixed partial derivative, right? You do this, you will get the same matrix. This is, and by the way, in finite element analysis this is commonly done. This is the energy formulation. And lastly, you have a force based approach where write down an expression for bending moment at any section considering a free body. Can we do this? Take a free body, and in terms of your stiffness coefficient, can we write an expression for bending moment? Right? See, your support reaction is K1 star J star, where and your end moment here is K2 star J star. If I cut a section here, the sagging moment expression, will it not take this form? That is first principles, right? Then I derive an expression for curvature by dividing my bending moment with EI, and from that curvature I integrate, I get an expression for slope. I integrate the expression for slope, I get an expression for deflection. I apply my kinematic boundary condition at the 2 ends. For each of those 4 cases, I keep doing this, apply the boundary conditions, put equilibrium, I will get the same matrix. I am not asking you to do all these 4 methods. I will be happy if you remember the physical approach, but now you see the power of understanding structural behavior. First principles, you have alternative paths to dealing with the same problem, and the wider and deeper your understanding, the more you will enjoy this subject. Is it clear? We have just put together all that we have learned till now. For a simple beam element, we will not repeat it for the space frame element, but it is the same logic. Is it clear to you? Okay. Now it is time to play games. We have to show how we can apply this knowledge to solving problems. Okay. As far as coordinate transformation is concerned, in the conventional stiffness method you do not have to worry at all, because what are the kind of beam problems you get? They are usually fixed, non-prismatic sometimes, continuous beams, beams with overhangs. The beauty is all of them are in one line. So it is like your axial element, but it is not one dimensional. Why not? Yeah, the definition of a 1D element is not only the element should be in one line, but so in axial forces you have 1D. So a beam is a planar element, because you have to bring in x and y coordinates, the loads are in the xy plane. Is it clear? So in a continuous beam system, the local x star and y star axes of any particular beam element with 4 degrees of freedom can be conveniently chosen to be aligned in the same direction as the global x and y axis. So it is like, so what is the advantage of this? Your TI, you still need it, but it is easy. What is a TI matrix? It is an identity matrix. Thus the 4 local coordinates numbered 1 star, 2 star, 3 star and 4 star can be directly linked in the global axis system as 1, 2, 3 and 4 to appropriate global coordinates which could be LMNP or whatever. So the compatibility is as shown here, and this is how you will write the transformation matrix. It is an identity matrix, you have to correctly write the global coordinates. In this case I have shown it as LMNP, it could be whatever you get in the structure. Okay. So the beauty about the identity matrix is the transpose of this matrix is also an identity matrix, and so if you try to convert the element stiffness matrix from the local coordinates to the global coordinates, you get back exactly the same matrix, except along with it you will get the linking global coordinates, which is crucial for you to do the slot wise adding. Okay. Is it clear so far? You see how when you first read about this slotting and all, you found it difficult to understand, but slowly now things are falling in place. But we went slowly. We first did axial elements which had only 1 degree of freedom, 2 degrees actually in the conventional stiffness method. Now you got 4 and bigger ones are on their way. So slow and steady. This is now a familiar playground. We have played soccer here quite a number of times. We are familiar with all the goal posts. Okay, you have the element level, you have the element level at local coordinates, element level in global coordinates. You are familiar with these transformations. This is the basic transformation Ti from global to local, and then if you take the transpose of that, you get from local to global, and then you have the diagonal, and then you have this is the transformation to get the element stiffness matrix in the global, and then all of them you should correctly put together and assemble the structure stiffness matrix. There is another method called using the displacement transformation matrix, where you directly deal with all the global coordinates in one go, but you will be dealing with big matrices. We will show both, but when you are doing programming, you are dealing with large structures, this is the way to do it. Okay. In your examination you have the choice, whichever you like you can do, but whenever possible do not do the conventional stiffness method, reduced element stiffness method. You deal with much smaller matrices, you can finish the problem much faster. Then you need to deal with equivalent joint loads. We are comfortable with beams because we have already done slope deflection method, moment distribution method, we know how to find fixed end moments. Only thing, we are now using the word fixed end forces because you also have to find the shear forces. Earlier we just found the end moments, now you need also the shear forces. Okay, so these are equivalent joint loads, and you know how to. You have another possibility, sometimes you have indirect loading. Okay, support settlements will cause indirect loading in reduced element stiffness method, not in this method, but you could get not so much in beams, but you could get in grids, or you could get in plane frames. You will have temperature effects, creep effects, shrinkage effects. So you will have to add any additional moment that you could get from indirect. In beams you will not get, in grids you can, in plane and space frames you can. Okay. Then you know how to do the shifting from the element level coordinates to the global level coordinates, that is all. Okay. And you can work out the equivalent joint load vector. So this is familiar terrain, we know the steps involved, let us just apply it. So we will do this together, one problem, and we will do it by both methods using Ti and Td in one go. So let us do it together. This is a fixed non-prismatic beam, both ends are fixed against translation and rotation, and you do not know the fixed end moments for this problem because it is non-prismatic, it has got all kinds of loads including a concentrated moment in the middle. Okay. The question is, can you draw the bending moment and shear force diagram? I find designers want that. Also, if possible, give us a maximum deflection here and there. Okay. So that is the complete problem. I do not need to write a problem statement because you know what we need. How do we proceed? Right, first you have to locate the nodes. So solution procedure, as before, we have to write down the global and local coordinates, number them, do the transformations, find the equivalent joint loads. You have two options. One is the conventional transformation matrix with the identity matrix, or you try the TD matrix, okay, and you have TDA and TDR. And if you are using the TD formulation, the fixed end forces you have to do using the summation for the two elements. Element and structure stiffness matrices, I am just reproducing what we did yesterday or the day before for axial elements. This part is all familiar, even this is familiar, we have done this. These equations are familiar. Here dr is 0 is O, it is a null vector because there are no support settlements in this problem, but if someone gave you support settlements, you say no problem, I just add it here. It is not at all an issue. Support settlement or rotational slip is no problem in this method because you can handle it in dr. So not a problem. But we have kept the question simple here. Then you find out from the first equation you solve and get the unknown displacements. Second equation you get the support reactions, and you use the unknown displacements to get your member forces. Is it clear? Method is same, only we are switching from axial element to beam element. The procedure is identical. Okay, if you are using TD matrix, there is a slight change. The slight changes between TI and TD show up in the first transformations. In assembling your structure stiffness matrix, it does not show up here, and it shows up finally when you get the membrane forces, otherwise the method is identical. Okay, so let us take our global coordinates. As usual, we will give preference to translation in the at the active degree of freedom. So 1 and 2, is it clear? 1 and 2, because only joint B can move, and we have separated out 2 prismatic elements, and 3 and 4 in that order are the support reactions restraint at the restraint coordinates, and 5 and 6 are also very easy to do, and we will stick to this. If you want to be a little different, okay, you put 4 and 5, 3 and 4 here and 5 and 6 there, it really does not matter. Okay, now what do we do? Local coordinates. But before we proceed, let us put the input data given. You are told that there are no support settlements, so dr is a null vector. You are told that there is one nodal load, you have a concentrated moment, remember in that problem, 30 kilonewton meter acting clockwise, so you should put minus, F2 is minus 30 kilonewton meter, F1 is 0, is this clear? And you do not know F3, F4, F5, F6, you have to find them out, they are your support reactions. So far so good, clear? Now local coordinates, you have 2 elements, both of them have the same span, 10 meter, they look alike, except the EI value is different. You have 2 EI for the first element and just EI. Do not plug in the EI value straight away because it gets eliminated, but if you want you can include it. Okay, so 4 degrees of freedom, very easy to do. Now what is your next step? Write down your TI matrix for the 2 elements, do it, they are all identity matrices, but I want to see the linking coordinates, that is all. Write the 2 transformation matrices. What will be the linking coordinates for the first one?
3, 4, 1, 2.
3, 4, 1, 2, and for the second one?
1, 2, 5, 6.
You said it, that is all, anybody can do this. Clear? Can we proceed? You just write the identity matrices and fill up, you can fill up in the row as well as a column, but the column is good enough, it is a square symmetric matrix. Is this clear? You have done the first step. If you want to do by the TD matrix, what will it look like? Can you give it a shot? TD, because let us do both methods parallelly. What is the size of the TD matrix? TD again you can subdivide into TDA and TDR, right? That is right. Now you fill it up, fill it up. This is the alternative approach, okay. So look at it this way, if I apply d1 equal to 1 and I do not allow any other movements in the structure, what will this affect? This will affect this displacement d1 equal to 1 in the global structure will cause this to also go up, right. d3 star in the first element will also be 1 and d1 star in the second element will be 1 and the rest will all be 0. So that's it. So when I put d1 equal to 1, d3 star will be 1 and d1 star will be 1, the rest will be 0. If I apply d2 equal to 1, d4 star in the first element will be 1 and d2 star in my second element will be 1 and the rest will be 0. Does it make sense to you? d4 star, d2 star? Likewise, okay. So and I have done a partition here because I am separating out the active degrees from the restraint degrees. Is this clear? Have you all got this? Easy to do. Two approaches. The advantage with this approach is you do not have to worry about the slotting. The matrix multiplication takes care of everything. Let us see both approaches, clear? And you should know both. Can I move ahead? Okay. Next you have to find fixed end forces, which you know the formulas. So first the reactions, 100 kilonewtons shared equally 50-50 and WL by 8. Remember when we did slope deflection and moment distribution, the left was minus, the right was plus. Now it will be reverse because anti-clockwise positive, so be careful. The left is plus and the right is minus because you have a downward mount. Those calculations are clear? You can fill up the first fixed end force vector, do the same thing, and you can also get the deflection if you want to. In your examination do not worry about this, but if you really want to, you know the formulas for finding deflection in fixed beams. For the other beams similarly you can work out, okay, WL squared by 12, right. You can, and the vertical reactions you can get 10 into 10 is 100 kilonewton acting downward, resisted by 50-50 up. So you get the second vector also. Is this clear? So you have got the element level fixed end force vector using the concepts that you are very familiar with. You can also get the deflected shape. In this case coincidentally both the peak deflections turn out to be the same, but that is just incidental, okay. So you have got the fixed end forces at the element level, you have to transfer them to the global level. So you have to just bring in those linking coordinates which we did, remember 3 4 1 2 1 2 5 6, the numbers do not change because you are multiplying with a identity matrix. And then now you do the slotting. So 1 and 2 go here, 1 and 2 go here, so these will add up and you will get this, 3 4 goes here and 5 6 goes here. Does it make sense? Does it make sense? That's something you have to do. This is a slotting thing, you have to put the right, once you have shifted to the global coordinates, global axis system, you are matching the element with the structure. Does it make sense? Clear? Okay. If you want to do the TD approach, that is straightforward. You got your TD, take the transpose, pre-multiply, you will get the same solution without doing any slotting. So this is in a sense easier, but you are dealing with bigger matrices, okay. Then find the net load vector, which is the nodal load vector minus the fixed end force vector. Remember this is your final nodal vector. Why are we putting minus? Because you artificially restrain those joints, they have accumulated, you have to let go of those restraints to get back your original loading condition. So you have got the net load vector. Element stiffness matrix, we know the formula, we have derived it, just plug in the values. In this case both spans are 10 meter, only the EI value is changing, EI value for one is 2 times the other. So you can write down these two, okay, K1 star and K2 star are cleanly obtainable from the formulas, both are prismatic, only EI is changing. So the inside part is the same, on the outside 2 EI by 10 and EI by 10. Next, you pre-multiply or you post multiply the element stiffness matrix with the transformation matrix. Now you bring in the linking coordinates, okay. Actually the transformation matrix is identity, so you really, there is no effort at all. I have just substituted the values of L here, that is all. So you get this, and then when you pre-multiply the whole thing with Ti transpose and you do the slotting business, you will get the full 6 by 6 matrix. Is it clear? Which you can partition as Ka, Kar, Kra and Krr, and K is of importance because this is the one you need to invert, right. If you want to use Td, do this and just add up the contributions from the two elements, you will get exactly the same matrix. Is it clear? You have two alternative paths. Then you substitute in your equations, find out your unknown displacements, plug in those values. If you want, you can look at the deflected shape. D1 is minus 37.7 millimeters. So minus means it went down and should have gone down anyway because the loads were all acting downward. And you had a D2 is a rotation, minus means it is actually clockwise, not anti-clockwise. Then you find the support reactions, the second equation, and write the correct units. The force is kilonewton, the moment is kilonewton meter. Draw a sketch and take a look whether the answers make sense. Does it satisfy equilibrium? Do a simple check on vertical equilibrium. This is something you have to do even when you use software, because sometimes you make big mistakes. So it is a quick check, you find total downward load is matching the total upward load. Find the member forces, okay, by using those equations. So you have got 4 answers for each element, 2 end moments and 2 forces, and with the help of that you can use Td and get exactly the same results. You finally draw shear force diagram, bending moment diagram, deflection diagram, which I think you are familiar with. So simple, and you can do more such problems of this kind. Thank you.